So this is 5D, the industrial manufacture of chemicals. We're going to concern ourselves with the dual award content. This all revolves around the Haber process. A little shout out to my A-level teacher. You pronounce it as Haber, technically named after Fritz Haber. I've just not kicked the habit yet. So what we're doing in this reaction is we're taking nitrogen and hydrogen. It's a reversible reaction to make ammonia. Haber process is a compromise of conditions of 200 atmospheres, 450 Celsius, and an iron catalyst. Three important conditions to remember. Sketching out the reaction vessels just now. A little complicated. So, first thing we need to know, where are we getting these materials from? Well, hydrogen can collect that mostly from the cracking of hydrocarbons. Nitrogen we get from fractional distillation of the air. First step in this process is to add these two into a mixer. So things are going to get mixed up here. We also filter out any particles that might have got in there that are not hydrogen or nitrogen. Moving up into the converter, here we're going to ramp things up to 200 atmospheres. Passing through into the actual reaction vessel, we're going to get these things reacting through. Heat up to 450 degrees Celsius, and we're passing that over the iron catalyst. There are all three conditions we need to remember. So our gases pass through, and eventually we get a little bit of ammonia made. Remember, this is a reversible reaction. We'll have a mixture of our reactants and our products. In this final chamber, we cool things down. We get ammonia in the liquid form, but we don't cool things down so much. We leave hydrogen and nitrogen in the gas phase. This means that we can actually recycle these back round, and so this process doesn't really end. It does mean that we're putting in hydrogen and nitrogen and getting out ammonia, our product. We're kind of cheating a reversible reaction. In terms of the conditions, we've mentioned that this is a compromise. As we look at the equation, we've got 1 mole of nitrogen and 3 moles of hydrogen. That's 4 moles of gas on the reactant side. And on the products, we've only got 2 moles of ammonia. So ideally, more pressure can push the reaction over to the product side. Your teachers may mention Le Chatelier's principle. The reason we picked 200 atmospheres is a compromise. Any higher pressure, the equipment gets very expensive. We've also got energy costs to think about as well. The temperature, 450 degrees Celsius. This reaction is actually exothermic going forwards. So ideally, we'd want as low a temperature as possible to push equilibrium to the right-hand side. However, if we do lower the temperature, the reaction takes a lot longer to go through. And so this is a bit of a compromise with the rates of reaction overall. Remember, we are recycling the unreacted gases, so we don't need to push equilibrium all the way to the right-hand side. The iron catalyst will speed up the rate of reaction in both directions. This is about time. The last thing to mention, the uses of ammonia. There are 3. Just need to know them, don't need to know any of the equations. First of all, manufacture of fertilizers. Second, making nitric acid, HNO3. And lastly, manufacture of nylon.